All right, so we want to solve the cart pull game or any other kind of game that is thrown at us, any kind of environment that we want to solve with our deep reinforcement learning algorithm. Well, so I've thrown some math up here on the board, but we're going to try to keep the math to a minimum. So bear with me here. We just need to cover enough kinds of terms that we can start writing our code, and the code will make some sense to us as we get going. So this is a diagram that I drew already earlier in these live lessons. This is the main concept of reinforcement learning. We have some agent, which is, in our case, going to be a deep reinforcement learning algorithm. This agent takes action in an environment, which in our case is the cart pull game. There's two possible actions that our agent can take. That's to move right or to move left. And then the environment provides the agent with feedback. So it provides two kinds of information as feedback. The first kind of information is the state. So this is the four pieces of information about the environment. So the location of the cart, the velocity of the cart, the angle of the pole, and the angular velocity of the pole. So these are the four states that are fed back. And then our reward that we're trying to maximize is to keep the pole upright for as many time steps as possible. So the more time steps we're up for, the larger the reward. So we can define this idea, this little diagram, we can define that more formally as this set of terms over here. So this paradigm, we can call it a Markov decision process. And the trademark of any Markov decision process is that we assume that the current state of the world at any given time step is representative of all of the time steps that have come before. So that's what a Markov decision process is. And then within our Markov decision process, we have this set of information. So this capital S represents all of the possible states. So in the cart pull game, this is all of the possible cart locations and cart velocities, angular pole angles, and pole angular velocity. So all of the possible states that it could have, each individual possible set of states is a lowercase s, and then the uppercase S is all of these states all together. Similarly, for the actions, a given specific action, so a specific move right or a specific move left, this is a lowercase a, and A is the set of all of our possible actions together, which in our case is just two possible actions. Most games have a much more complexity. R is the distribution of the possible rewards that we can get back given any single state and action. So at any given time point, we can have an action that's taken and a state. So given the pair of these two states, what is the distribution of the reward? So what's the possible rewards that we could get given a state and an action at a given time step? P is the transition probability distribution of the next state. So this is given the last state and the action that we take in that state. This transition probability is the distribution of the states that we'll get next. So the algorithm, the agent, it gets a state. So this would be like the starting state of the environment or some state later on after we've started playing the game. The agent takes some action, and P is the probability, it's the distribution of probabilities for the state in the next step. And then finally, the last term in this Markov decision process that we need to talk about is gamma, this discount factor. The discount factor is a hyperparameter that we set ourselves, and this is how much we want the agent to discount future reward. So when our agent is considering any given action to take in the environment, it's going to try to take the action that maximizes its reward. The further that it tries to predict future reward, the less likely that reward is. So, if you can imagine this kind of scenario where where the algorithm is thinking several steps ahead, and the very next step, it might have a pretty good sense of what kind of reward it's going to get. But then the further into the future those steps become, the more difficult it is to guess what the reward will be. There's more uncertainty. So this discount factor captures that. And so what this means is that the expected reward in the next time step is valued more highly than the expected reward in 2 time steps, 3 time steps, 4 time steps. So the further we try to predict into the future what our reward will be, the more discounted that reward is. So given any set of states, our goal here is to to identify a policy that maps our states to our actions. So given some states, we want to have this overall policy of what kinds of actions we should be taking in those states. So it could be the case that in some kind of states, it's very clear exactly what kind of action we should take. And then in that case, it's relatively simple for the algorithm to identify a policy. But the more complex the game is, the more possible states that there are, the more uncertainty there is about what reward will be given in the future, the more complex this policy function is. So this policy function is the thing that we're trying to learn with our deep reinforcement learning algorithm. You can imagine that there's some kind of, with this cart pull game, if we're in a state where the pole is actually perfectly balanced on top of the cart, then the policy in that particular situation is pretty easy to define. The best policy is to stand still. The pole is balancing perfectly, so let's just stay in one place. We don't want to move to the right or to the left. But when the game starts, the pole is on some angle, and so we need to figure out, okay, how many steps should I move to the left to get the pole to stay upright, to keep us from dropping the pole. And so there's all these kinds of different kinds of states that we can have in the environment, all these different configurations of the cart with the pole on top of it, and how quickly the cart's moving, how quickly the pole's moving, all these various states. We need to come up with this overall optimal policy of what action to take. And that's how we win the game. So our objective is to find the policy star, the optimal policy. And we can define this mathematically as the maximum expected cumulative reward. So we're trying to maximize our reward, and we're discounting future rewards. So that's why we multiply our rewards by the discount factor. And then we're just summing them together. So our policy, our optimal policy here is to identify the perfect policy that guarantees that we'll maximize our reward given any particular state of the game. So that's overall what we're trying to do here. I'm going to throw a couple more equations at you next to define this a little bit further.